According to the most widely used definition of acids and bases, an acid is a chemical entity capable of donating a proton, while a base is a chemical entity, chemical species, capable of accepting a proton. For instance, when gas hydrogen chloride is dissolved in water, the following process takes place. 1 mole of hydrogen chloride donates 1 mole of protons to 1 mole of water and turns into 1 mole of chloride ions, while the water turns into 1 mole of the so-called hydronium ions. Now, hydrogen chloride donates a proton, therefore, according to the definition, it is an acid. Water accepts a proton, therefore, according to the definition, it is a base. Notice that in order for a species, for a chemical entity to realize itself as an acid, there must always be another entity that has to realize itself as a base. Even more interesting is the fact that when a chemical entity realizes itself as an acid, it always creates its own conjugate base. That is, a species that has the potentiality to act as a base, to accept protons. In this instance, the chloride ions are the conjugate base of the hydrogen chloride dissolved in water, which is the acid. On the other hand, the hydronium ions are the conjugate acid of the water, which is the base. Notice that in this definition of acids and bases, only the ability of the species to donate or accept protons is mentioned, and not how easy or how difficult it is for these species to accept or donate protons. Similarly, when ammonia gas is dissolved in water, it acts as a base, accepting a proton from the water molecule and turning itself into its own conjugate acid, the ammonium ion. The water donates a proton to the ammonia and turns itself in its own conjugate base, the hydroxide ion. In this instance, the water molecule acts as an acid, since it donates a proton. By the way, notice that the water molecule acted as a base as well as an acid, depending on the conditions of the process. Substances that can act both as acids and bases, depending on conditions, are called amphoteric substances. Water is an amphoteric substance. It can accept as well as donate a proton, depending on conditions of the process. In one unique but very important case, water can act both as an acid and as a base during the same process. This happens during the so-called autoionization of water. In it, 1 molecule of water donates a proton to another molecule of water. Thus, the first molecule qualifies as an acid. In the process of donating the proton, the first molecule creates its own conjugate base, the hydroxide ion. The second molecule of water, the acceptor of the proton, acts as a base, and in the process of accepting of the proton, it creates its own conjugate acid, the hydronium ion. We can simplify these equations by just indicating that the acid releases a proton, and of course an anion is formed, while the base accepts a proton, thus forming a positive ion. water is split into a proton and a hydroxide ion. Now this single arrow in the equation of hydrogen chloride dissolved in water indicates that no intact species of hydrogen chloride exists in water anymore. All of the HCl is split, ionized into protons and chloride ions. On the other hand, when ammonia is dissolved in water, only very few of the ammonia molecules accept the proton and turn themselves into ammonium ion. Therefore, a dynamic equilibrium is established between the ionized and non-ionized species of ammonia. Similar is the case with water molecules. Only very few of the water molecules undergo autoionization and turn themselves into protons and hydroxide ions. Most of the water molecules remain intact. So there's a dynamic equilibrium between the ionized and non-ionized species in water. It is seen from the last equation that in pure water the number of protons equals the number of hydroxide ions. It is known from experiment that in pure water the concentration of the protons, the molarity of protons, which equals in pure water the concentration of hydroxide ions, or the molarity of the hydroxide ions, is equal to 1 times 10 to the minus 7th molar. Remember that in these square brackets we always denote molarity of species. The perfect balance between the number of the protons and the hydroxide ions in pure water, or in other words, the molarity of the protons and the molarity of the hydroxide ions in pure water, makes the reaction of the water neutral. Now we will introduce an arithmetic simplification which is widely used in chemistry. Thus, instead of writing the molarity of the protons as 1 times 10 to the minus 7th molar in exponential notation, we will take the negative logarithm of the molarity. Which is equal to minus logarithm of 1 times 10 to the minus 7, and this is equal to 7. We will call this negative logarithm pH. This pH equals 7. At first, it may seem like an unnecessary complication, but eventually it will be appreciated that it is much easier to handle positive numbers rather than the cumbersome numbers in scientific notation. Of course, we can apply this so-called P function, which is taking the negative logarithm, to the molarity of the hydroxide ions, and we can obtain POH. Also, the P function, that is taking the negative logarithm, can be applied to any other quantity expressed in scientific notation, in exponential form. Here's another example for the convenience of the P function. Suppose that the molarity of the protons is 1.3 times 10 to the minus 4th, then pH will be the negative logarithm of this number, and it's equal to 3.89. This is a positive number, much easier to work with than this cumbersome number expressed in scientific exponential notation. Now let us see how we use a calculator to take the negative logarithm of this number. This is a typical calculator. Your calculator may differ a little bit. If so, consult the manual that comes with it. So we press 1.3, then the button EXP, which stands for exponent, then plus minus 4. Notice that this button plus minus differs from the main plus and minus buttons. And then the button LOG, which stands for logarithm. To make the number positive, we press again plus minus. Now we see that there are too many numbers here on the LED of the calculator. How many of these numbers are to be retained? Now the rule is that the logarithm of a number has as many digits after the decimal point, this is called mantissa, as are the number of significant figures in the original number. Now the original number has two significant figures, as can be seen. Therefore we retain only two significant figures in the mantissa of the logarithm. As you can see, the second number is rounded. Now notice that 1 times 10 to the minus 7th is a smaller number than 1.3 times 10 to the minus 4th. Therefore, the concentration of the protons, the molarity of the protons in the first case, is lower than the concentration, the molarity of the protons in the second case. However, the pH in the first case is a larger positive number than the pH in the second case. In other words, the lower the concentration of the protons, the higher the pH. The higher the concentration of the protons, the lower the pH. It's interesting to see how the anti-logarithm of a number is taken. Suppose we're given pH 3.89 and we're asked to determine what the molarity of protons, what the concentration of the protons is. Then we press 3.89 minus, and then there's a button which on some calculators says second or INV, which stands for inverse, and then we press log and we get this number on the LCD of the calculator, 1.288249552 times 10 to the minus 4th. Too many numbers. How many of these numbers are to be retained? The rule with the anti-logarithms is that the anti-logarithm of a number has as many significant figures as the digits in the mantissa of the logarithm. Here we have 2 digits in the mantissa, therefore we retain 2 significant figures in the anti-logarithm. Now let's go back to the ionic equilibrium in water. We may write the equilibrium constant, and in the expression of the equilibrium constant we notice that the concentration of the water molecules is constant, and it can be included into the Kc. This we obtain Kw. This is the so-called ionic product of water, and as we already mentioned, the concentrations, the molarities of the protons in the hydroxide ions are 1 times 10 to the minus 7th, both. Then we may take the logarithm of the ionic product of water, which will be the sum of the logarithms of the protons, of the concentration of the protons and the hydroxide ions. Now, of course, we can multiply both sides by minus 1. Minus 1. And as we see, this gives us pH plus pOH. You can see again the expression for the negative logarithm of the ionic product of water, which is the sum of the negative logarithms of the molarities of protons and hydroxide ions. In other words, the sum of pH and pOH. Now, if we have pure water, as already noted, the molarities of the protons and hydroxide ions are equal to each other, and experimentally it's determined that they are 1 times 10 to the minus 7th. When we take the negative logarithms of these molarities, we obtain pKw equals to 7 plus 7, that is 14. It is important to understand that the sum of pH and pOH is equal to 14 at room temperature, not only in pure water, but in all aqueous solutions, water solutions. After all, Kw, pKw, respectively, is an equilibrium constant. And as any equilibrium constant, its value should be, as the name suggests, should be a constant for a given temperature. Nevertheless, however, the constancy of 14 can be maintained in different ways. For instance, the concentration of the protons can be 1 times 10 to the minus third. Therefore, the pH will be 3. Negative logarithm of this value will be 3. In order to maintain the constancy of pKW equal to 14, pOH has to be 11. Now, this, however, leads to violating of the balance between the protons, the molarity of the protons, and the molarity of the hydroxide ions. Number of protons is not anymore equal to the number of hydroxide ions. Protons are much more here. The concentration of protons is much higher, orders of magnitude higher. Therefore, in this case, the reaction of the solution is acidic. And still, Kw and pKw is 14. In other words, when a species capable of releasing protons, such as hydrogen chloride gas, is introduced in water, the balance between the protons and the hydroxide ions is disturbed in favor of the protons. In this case, the reaction of the solution will be acidic. On the contrary, if a substance such as ammonia gas capable of accepting protons is introduced in water, the balance between the protons and the hydroxide ions is disturbed, however this time in favor of the hydroxide ions. Now the reaction of the solution will be basic. Acids are such species that cause the protons to prevail over the hydroxide ions in aqueous solutions. The opposite is true for bases. If the number of protons and hydroxide ions in a solution is equal, as already mentioned, the reaction of the medium is neutral. Next comes the question of strong acids and bases. An acid or a base is considered strong not because it is concentrated. In other words, not because the number of moles of this acid or base in 1 liter of solution is high. There are dilute solutions of strong acids and bases, but because the number of ionized species in the solutions of strong acids and bases is much higher than the number of non-ionized species. As a matter of fact, strong acids and bases are practically 100% ionized. From this, it is immediately obvious that the concept of equilibrium constant is irrelevant with regard to strong acids and bases. For instance, we can observe the ionization of hydrochloric acid to protons and chloride anions, and we can write formally an expression for an equilibrium constant. Now we see from this expression that the concept of equilibrium constant is irrelevant in the case of a strong acid. Indeed, in the denominator we have the concentration of hydrogen chloride, which is 0, as we already know. Therefore, this expression is a mathematical absurdity. Thus, for strong acids and strong bases, the concept of equilibrium constant is not applicable. These are the most widely used strong acids and strong bases: perchloric acid, hydroiodic, hydrobromic, hydrochloric, sulfuric acid, and nitric acid. And strong bases: sodium hydroxide, potassium hydroxide, lithium hydroxide, and barium hydroxide. You may notice that sulfuric acid, for instance, has 2 protons to donate per mole of sulfuric acid. That's why it's called a polyprotic acid. Also, barium hydroxide can donate 2 hydroxide ions per mole of barium hydroxide. That's why this is a polybasic substance. As far as weak acids and bases are concerned, although weak, they still can vary in strength. The larger the equilibrium constant, or the acid, respectively base, ionization constant, the greater the strength of the acid or the base. For instance, if we have acetic acid and hydrocyanic acid, we see that acetic acid has 1.8 times 10 to the minus 5th acid ionization constant, while the acid ionization constant of the hydrocyanic acid is 4.9 times 10 to the minus 10th. Much lower. This means that the products, that the ions that are produced by this ionization are much less compared to the ions in the case of ionization of acetic acid. Therefore, acetic acid is a stronger acid compared to hydrocyanic acid. Again, the greater the value of the acid or base ionization constant, the stronger the acid or base. However, look at the negative logarithm of the ionization constant, the pKa, that is. The lower the pKa, the stronger the acid. It is interesting to see how one calculates the concentration of protons, respectively the pH, in the case of a weak and a strong acid. And this can best be seen if the strong and the weak acid are of the same molarity, for instance, 0.1 molar. In the case of a strong acid, such as hydrochloric acid, for instance, this calculation is pretty straightforward. From the ionization equation, we see that each mole of hydrochloric acid turns into 1 mole of protons and 1 mole of chloride ions. Therefore, 0.1 mole of hydrochloric acid will turn into 0.1 mole of protons and 0.1 mole of chloride ions. And because we're interested in the protons, pH will be the negative logarithm of the molarity of the protons, that is negative logarithm of 1 times 10 to the minus 1st. Therefore, it will be 1. For a weak acid, such as acetic acid, the calculation of the molarity of the protons in 0.1 molar solution may be a little bit more involved. However, it can easily be done once one realizes that the molarity of the protons participates in the expression for the equilibrium constant, or the so-called acid ionization constant of this ionization reaction. And second, if one realizes that each 1 mole of the acetic acid that is breaks up into 1 mole of acetate and 1 mole of protons. Therefore, at equilibrium, the molarity of the acetate equals the molarity of the protons, which we may denote by X, and we may substitute in the expression for the equilibrium constant, or the acid ionization constant. This will be X times X, these are X times X, over, now the initial concentration is 0.1 as we mentioned, and due to the breakup of these acetic acid molecules is decreased by an amount of X. We can rearrange this expression and a quadratic equation is obtained. This is the standard formula for the roots of a quadratic equation. And now all we have to do is identify the coefficients A, B, and C in the quadratic equation and substitute them in this formula. Coefficient A is 1, coefficient B is 1.8 times 10 to the minus 5th, and coefficient C is minus 1.8 times 10 to the minus 6th. After substituting all these numbers here in the expression, we obtain two roots, one of which is negative, and of course we will neglect it for physical reasons. Now recall that X is the concentration of the protons. This way we obtain the value of the concentration of these protons. And of course, we may calculate the pH, which is negative logarithm of this concentration. Which is 2.89. In conclusion, we see that a 0.1 molar solution of a strong acid, hydrochloric acid, maintains pH equal to 1, while the same concentration, 0.1 molar, of a weak acid, acetic acid in this case, maintains a higher pH of 2.89. This is exactly what we expected. Acetic acid is a weak acid, and it maintains a lower concentration of the protons. Therefore, the pH is higher. Now that we know how much the pH of 0.1 molar acetic acid solution is, it will help us in calculating the ratio of the equilibrium concentration of the acetate over the equilibrium concentration of the acetic acid. What's the point? Why do we want to know this? It will become clear shortly. In the meantime, let us do the following. Let us express the concentration of the protons, the molarity of the protons, from the expression of the equilibrium constant, of the acid ionization constant. It will be Ka times CH3COOH over CH3COO. Now we can take a logarithm of both sides of this expression. And then we can multiply by -1 both sides. And we'll obtain minus logarithm minus logarithm of the molarity of the protons is pH. This is pK. Okay. And this minus logarithm, if we reverse the places of the denominator and the numerator, this will become plus logarithm of CH3COO over CH3COOH. We can substitute in the last expression pH 2.89 and for pKa 4.74 plus logarithm CH3COO and now we can rearrange this expression and we'll obtain the logarithm of this ratio equal to minus 1.85, and then we can take the anti-logarithm, we already know how, and we find out that the ratio between the molarity of the acetate ion, equilibrium molarity, and the equilibrium molarity of the acetic acid is equal to 0.014, approximately 1/71st. This calculation shows that the concentration of the ionized species of the acetate in 0.1 molar solution of acetic acid is only a fraction of the available acetic acid in the solution. The concentration of the intact acetic acid, of these molecules that have not been ionized, is over 70 times larger than the concentration of the ionized species. This quantitative conclusion about the ratio between the ionized and non-ionized species in 0.1 molar solution of acetic acid is interesting. However, we will use it shortly for something more important. We will modify this ratio to enable the solution to resist the change of pH. Speaking of resistance to change of pH, let us first explore how will the pH value change upon the introduction of 0.01 liters of 1 molar hydrochloric acid in 1 liter of pure water, which has, as we know, pH 7. Now we write number of moles of hydrochloric acid introduced is equal to 0.01 liters times the molarity of the hydrochloric acid, which is 0.01 moles. Here we have the molarity of the protons after the addition of this amount of hydrochloric acid is equal to 0.01 moles over 1 liter plus the increase in volume, which is 0.01 liters. And this is equal to 9.9 times 10 to the minus third molar. This corresponds to pH 2. Now we see that upon introduction of this amount of hydrochloric acid, the pH changed 5 pH units, from 7 to pH 2. This means that the concentration of protons after the introduction of the hydrochloric acid increased 100,000 times. This is an enormous change. Therefore, the pure water exerted practically no resistance to change of pH. Is there a way to prepare solutions that would resist such a dramatic change in pH? Indeed, such solutions can be prepared. Solutions that resist change of pH are called buffers. Where to start, however? How are we to prepare such solutions that resist change of pH? Now, the first thing that comes to mind is that since resisting of change of pH is in fact sustaining the existing balance between the protons and hydroxide ions in a solution, in this solution, in a buffer solution, there has to be species that would immediately bind any incoming protons as well as any incoming hydroxide ions and would neutralize them. Now the time came to utilize the promised modification of the ratio between the acetate ions and the molecules of the acetic acid in the solution. As we already saw, this ratio in 0.1 molar solution of acetic acid is 1/71. Let us change it into 1/1 by deliberately introducing a source of acetate ions. A source of acetate ions can be the salt sodium acetate. The salt sodium acetate can be obtained by the neutralization reaction between acetic acid and sodium hydroxide. Now this salt is an ionic salt, therefore every mole of it dissociates, splits into ions in solution. into acetate anions and sodium cations. Now, this is the main source of acetate ions in the solution. There may be a slight contribution to the number of acetate ions from the equilibrium established by the acetic acid itself in the solution. However, due to our deliberate introduction of acetate ions, the numerator of the acid ionization constant will increase. This will lead to the increase of the value of the acid ionization constant. However, acid ionization constant is an equilibrium constant. Therefore, it has to maintain a constant value corresponding to a given temperature. In order for this value to be re-established, the numerator has to increase in value too. Therefore, this equilibrium shifts to the left. In other words, the ionization of acetic acid is suppressed due to our introduction of acetate ions. So if we add a tangible amount of acetate, say by placing of 0.1 moles in 1 liter of sodium acetate, then sodium acetate can be considered practically the sole contributor of acetate ions in this solution. We can now use the already derived expression for the pH of such solution with the modified ratio between these components. Now we have 0.1 molar acetate over 0.1 molar acetic acid. It's a 1-to-1 ratio. Logarithm of 1 is 0. So we obtain pH of this prepared solution is 4.74. Now we can check what the resistance to change of pH is of the buffer solution we just prepared. So let us add the same amount, 0.01 liters, of the same 1 molar hydrochloric acid. As soon as the protons of the hydrochloric acid appear in the solution of the buffer, they're immediately neutralized by the available free acetate and are turned into acetic acid. Acetic acid is a weak acid. It holds on to its proton and doesn't give it off easily. It's only logical then that its own conjugate base will be a strong base. As long as there's a free proton around, it will immediately accept it and turn back into its own conjugate acid. Therefore, from this example, we see that the conjugate bases of weak acids are strong bases, and vice versa. The conjugate acids of weak bases are strong acids. Let us get back to our calculation. Due to the addition of the hydrochloric acid, the equilibrium concentration of the acetic acid will increase, while the equilibrium concentration of the acetate ion will decrease in proportion to the incoming protons. Now we can calculate the pH of the buffer after the addition of the hydrochloric acid, and we see that here the concentration of the acetate ion is 0.09, while the concentration of the acetic acid is 0.11. This gives pH of 4.65. This pH of 4.65 is only 0.09 pH units lower than the initial pH of the buffer before the addition of hydrochloric acid, which was 4.74. This shows how strong the resistance of the buffer is against the change of pH, unlike the resistance of pure water. Now that we already understand how the resistance to change of pH is achieved in a solution, another interesting question appears. What will be the pH if we add sodium acetate into pure water rather than in a solution of weak acid? We already know that because sodium acetate is an ionic salt, it dissociates entirely into ions in a water solution. However, this process takes place in an environment where there's also this equilibrium, the process of ionization of water. According to these equations, there must be a coexistence as separate species of 4 different ions, the acetate, sodium, proton, and the hydroxide ion. Indeed, the sodium and the hydroxide ions can coexist as separate entities in the solution. As soon as the acetate ions appear in the solution, they immediately bind with the protons from this equilibrium, as has been said many times already, and form with them acetic acid. Now, the acetate ions, of course, act as a base here, therefore we can write the base ionization constant. It is immediately obvious that due to this binding between the acetate ions and the protons, the balance between the protons and the hydroxide ions is disturbed in favor of the hydroxide ions. Therefore, in this instance, the reaction of the medium will be basic. Observe that sodium acetate is a salt that can be produced by the reaction of a weak acid and a strong base. All salts that can be produced by a reaction of a weak acid and a strong base, when dissolved in water, disturb the balance between protons and hydroxide ions in favor of the hydroxide ions and cause the reaction of the solution to be basic, of pH over 7. As it was shown at the beginning of the lecture, we can write this reaction as the reaction of the acetate ion with water, and now we can clearly see the production of the hydroxide ions. On the contrary, dissolving in water of a salt that can be made by the reaction of a strong acid and a weak base causes the pH of the solution to go down below pH 7. In other words, the reaction of the solution becomes acidic. Salts that can be made by the reaction of a strong acid and a strong base do not disturb the balance between protons and hydroxide ions when dissolved in water, and therefore do not change the pH of the medium. The phenomenon of disturbing the balance between the protons and the hydroxide ions when dissolving salts in water is called hydrolysis. This is the end of this lecture. It is hoped that in understanding the discussed principles, the commonality between the different acid-base systems will become more obvious, and this will simplify their analysis. For instance, the theoretical basis behind the various titrations between weak and strong acids and bases can be viewed as just a review of the discussed principle. Also, once the discussed principles are understood, it is very easy to make them more precise by considering activities of ions rather than concentrations.